pressure. A student is investigating the boiling point. So allow me here to highlight how the boiling point of a salt solution varies with pressure. In this paper, you shall see that we shall meet mainly these two things. How A varies with B. How A varies with B. That's most of our investigations. Investigating how A varies with B. So here we're investigating how the boiling point of a salt solution varies with the pressure. It is suggested that the relationship between the Celsius temperature at which the water of the solution starts to boil, so the Celsius temperature theta, and the air pressure P. Remember, we are investigating the boiling point of a salt solution, how it varies with pressure. So now there's a suggestion that the Celsius temperature theta at which the water starts to boil and the air pressure P is given by that equation. Theta is equals to K sigma P to the power of Q, where sigma is the density of the solution and K and Q are constants. Then here's the question. Design a laboratory experiment to test a relationship between Q and P. So we are going to test a relationship between Q and P. Theta and P, Theta being the Celsius temperature at the boiling point where the solution starts to boil, and P being the air pressure at that particular moment. Explain how your results can be used to determine values of K and Q. So now, let's go to where we will start to write this question. So we need firstly to identify, the first step every single time is to identify who is the independent variable and who is the dependent variable. And by independent variable, what do we mean by independent variable? By independent variable, we mean the variable that is not dependent on the other variable, because there are two variables in this case. There is the boiling point of salt solution, and then there is the pressure prevailing at that moment. So even when you read this question, you can easily see it. A student is investigating how the boiling point of salt solution varies with the pressure, meaning that there is an air pressure which is there at that particular time, and then we are going to have a boiling point of the salt solution. So in other words, the one who is being changed first is the air pressure, and then the boiling point of salt solution will change. So we want to know, how does the boiling point of a salt solution varies with the pressure? Even in this question, it is so clearly, as the question is asked in that order, that the boiling point is dependent on the pressure. So pressure is the independent variable and boiling point is the dependent variable. So it is important to identify this thing. So what do? You come and you write it. Variables. P is the independent variable. They know already that P is the air pressure in the question because P is given in the question. Theta is the dependent variable. So the next thing, what you must identify is the control variable. And by control variable, we mean what must be kept constant. What must be kept constant in this experiment? Because when you are doing an experiment, you want to make sure that you are determining how an independent variable causes the dependent variable to change. For example, an independent variable might be inversely proportional to the dependent variable. They might be exponential. They might have an exponential relationship. They might have a direct relationship. They might just have a linear relationship. We do not know all of these things. So the goal is to find the relationship between the dependent and the independent variable. So we want to make sure that nothing else will affect the dependent variable, so that the dependent variable, any change that happens in it, is being influenced by the independent variable. So in this case, how do you identify who is the independent and who is the dependent variable? It's usually very easy. Take consideration in this experiment. In this equation, theta and P, we already know that these two, theta and P, are the independent and dependent variable. And then we are also told that K and Q are just constants. So K and Q are just constants, meaning that K and Q, there is nothing that we can do much to K and Q. They are already constants, so they are not going to affect the dependent variable. So we are left with this sigma here. So we are left with this sigma. So the sigma is something that we must keep constant as given by that equation. It's something that can affect the boiling point, the temperature, Celsius temperature at the boiling point. Okay, so then we move on to the next stage. So as you can see, in this variable stage, we have identified the variable, keep constant the density of the solution, sigma, as you can see. So sigma, in this case, was representing the density. Now the next stage, by this time you have not even drawn the diagram. So the next stage, what do you do now? The next stage, you need to now tell us the procedure of how you're going to do the experiment. Now, when you're telling us the procedure of how you're going to do the experiment, what must you say? You need to tell us what must happen for you to be able to measure the independent variable, number one. What must happen for you to be able to measure the dependent variable? What must be used to measure the independent variable? And what must be used to measure the dependent variable? That's step number one in the procedure. So as you can see here, as I will read step number one in the procedure, I'll read the processes that needs to be done that facilitates us to be able to measure the independent variable and to measure it and the apparatus to be used, and the processes that allow us to measure the dependent variable and also the instruments to be used. So I'll read. Heat the solution within a sealed container using a Bunsen burner. Now you might wonder, why are we even talking about a sealed container? I'll go back to heating of the solution. Why are we talking about a sealed container? I'm talking about a sealed container because already I've thought about the issue that we really want to know how air pressure determines the boiling point of a salt solution. So if we need to know the air pressure, it cannot be air pressure which we cannot control. We want to have the salt solution inside the container such that this salt solution, when it's inside a container, above it there will be air. And this air pressure is not influenced by atmospheric pressure, so that's why we have a sealed container. Number one. Then the next thing is I have in this statement indicated that we are going to heat this salt solution. Why are we heating the salt solution? Because we want it to boil. Ultimately, we want it to boil at a particular pressure. We want it to boil. So if we want it to boil, then we are going to have to heat it. How are we going to make it boil and have to measure the temperature, the Celsius temperature at the boiling point if we have not made it to boil? So as you can see, this is the procedure which is telling us how we are going to be able to measure the independent variable, how we are going to be able to measure the dependent variable. We are talking about the steps needed, what must be done so that we can be able to have an independent variable that is measurable and the dependent variable that is measurable. And also I mentioned the apparatus to be used. In this case, I talked about the Bunsen burner. You could have used an apparatus, but I feel that the Bunsen burner is the best apparatus to use in that case. Then next I talk about how I'm going to be able to measure now the pressure above the solution. In this case, I just talked about the apparatus. Usually, unless if it involves a process which is needed to measure P, you don't need to talk about the process unless if it involves a process. In this case, I just need to measure the pressure P above the solution using a pressure gauge. Then next, I talked about how I'm going to measure the temperature of the salt solution. So use a thermometer to measure the temperature theta when salt solution starts to boil. But it's important also now to indicate, because this person this is more like a design of an experiment which you are designing for someone to do. So they will need to know when boiling has started. How do they know that boiling has started? Such that they can then note that temperature theta at which boiling has started. They can only know this by noticing when temperature stops changing. I believe we should know that at boiling, just like at melting, temperature does not change. So it is important to mention this in our procedure, that because it was part of the thing that we need to be able to measure the Celsius temperature theta when boiling starts. So we must mention how do we identify that boiling has started. Now, having talked about how this experiment is going to be performed, how we are going to be able to do whatever we need to do to be able to measure the independent variable and to be able to measure the dependent variable also. Now, we then talk about the procedure of doing the experiment continuously now. How we are going to change. Because whenever an experiment is done, we are not just going to have one value of pressure and one value of Celsius temperature. The two cannot give us a relationship. We need several values of theta and several values of P. So to do that one now, we need to be able to vary. And in which case, whom are we going to vary? The independent variable is the one that we will vary. So you must explain in your process, how do you vary the independent variable? In this case, I said, use a pump connected to the sealed container to vary the air pressure P. There's no need to be more elaborate than that. A pressure pump, you have gone with a car to the filling station whereby you can fill up the tires with the air pressure. So the same thing can be done here. We have pressure pumps which can be used to fuel up a bowl. The same thing, very simple gadget. You don't need to over-explain this. This is as far as it goes. Use a pump connected to a sealed container to vary the air pressure. Gradually increase the pressure P. So in other words, we want to have several values, right, of P. And for each value of P, we need to have a value of theta. But when we are increasing the pressure, there is no point in increasing the pressure too quickly, as it can have some detrimental effect to our experiment, how it is being done. You can just change the pressure. You just need a new value of pressure P, and then you measure the boiling point again for the new air pressure on top of the boiling water. So gradually increase the pressure P. For 6 different values of P, find theta. So usually in physics, all physics experiments, we must have at least 6 sets of readings of the independent variable against the dependent variable. In this case, we are going to have values of P and theta. So this was the procedure of how we are going to do the experiment until we have values of P and values of theta, so that now we are able to determine the relationship between the two. Of course, we'll talk about how then do we determine the relationship between the two in the analysis stage. But we are still on the procedure now. Now, remember, we talked about keeping density constant. But how are we going to keep density constant? It is important that we keep density constant. When do we need to keep density constant? Remember, this experiment is being done 6 different times. Each time we will change the air pressure. But there are also always risks involved. Maybe we might have a salt solution already inside the container. But when it is boiling, there is every chance that some of the salt solution will change into into water vapor. Some of the salt solution will change into water vapor. This can increase the density of the salt solution in this case. So in as much as even if you were to change air pressure, in which case on top of the salt solution there is already some vapor which is already filling that place already. So it will affect the experiment. So it will be wiser for each experiment, each time when you want to have a new air pressure, to start from afresh with cold water again, cold water salt solution. It is better to start that way. Otherwise, it will be prejudicing the experiment. So now, how do we ensure that all the salt solution that we are introducing into the sealed container is of the same density? We need to be able to measure the density, number one, because you cannot be able to control a control variable, to keep something constant if you don't know its value. How do you keep something constant if you don't know its value? So firstly, you should be able to measure the value of something so that then you can say that I have kept it constant because I kept its value at this value. So density of solid solution, how do you measure it? Firstly, we need to find the volume of the solid solution. So you need to mention the apparatus. So keep the density for each experiment by using a solution of the same density. How? Calculate density using the formula rho is equals to mass over volume. Use measuring cylinder to measure the volume, and difference difference inside readings. The difference here in this case is the difference that you find in the readings of the measuring cylinder with solution and the measuring cylinder without the solution. Why? Because that will give you the actual mass of the solution. But you must tell us also the apparatus. In this case, you are using a scale. So the difference in scale reading of the readings of the measuring cylinder with the solution and the measuring cylinder without solution to measure the mass of the solution. So after finding the mass of the solution, after finding the volume of the solution using the measuring cylinder, in both cases you mention the apparatus to be used, then you find the density rho. So, but the question is, what do you do when you have mixed salt and water and you have realized that, okay, the density may be at that particular moment is less than the desired density or is above the desired density? What do you do? Because that might be the case of what might happen when you have mixed and you have measured the mass, you have measured the volume, you have calculated, you have seen that the density of the solution is more or it's less. So to have the same density for each experiment, you add salt to increase the density if it is less than the desired density, or you add water to decrease the density, that is if it is more than the desired density. So that way we can keep the density of the salt solution constant. So now in this case you have finished the procedure. You have told us how the experiment is going to be done. Number one, to be able to measure the independent variable, to be able to measure the dependent variable. That was the first process. Then the next thing now, you told us how then you're going to vary the independent variable so that you can get 6 sets of readings. Then finally, you told us how you are going to keep the control variables. In this case, what must be kept constant? Constant. So in that case, you would have finished with the procedure. Now, when you're finished the procedure, then you can go back now in the space for the diagram. Because now it is always important to write procedure first, because as you're writing the procedure, you're thinking of apparatus, you're thinking of several things, what is needed to measure this and this and this. This allows you to think in a linear way and allows you to be able to know the diagram that you must draw. Now, my diagram that I drew here probably is too perfect, but you must have a similar diagram. For example, here I indicated with the box, I indicated a pressure pump. Now someone will be worrying about how to draw the pressure pump. I indicated on the pressure pump a digital scale to show the pressure gauge, which will tell us the pressure P. I also have the salt solution, so it is not written well here. I wrote solution, but it's supposed to be written what? Salt solution. I also have the Bunsen burner there, and I have the thermometer there. So that's a nice diagram. Of course, this is a tripod stand, but sometimes it's not necessary to label some of these things, but just label them. And of course, this is the workbench. Okay, so having drawn the diagram, which might have 1 or 2 marks, now we go to analysis. Remember, we need to analyze now. Suppose this person has obtained 6 sets of readings. In this case, they have obtained 6 sets of readings of theta against and the pressure. They need to analyze their readings to ensure that these readings obey. Remember, we are investigating whether they obey the relationship that we were given. The relationship was saying theta is equal to k sigma p to the power of q. So if they obey this relationship, then certain conditions must happen. For instance, we know that for the relationship theta is equal to k sigma p to the power of q, using logarithms, using logarithms, applying the logarithm to both sides of this equation, we are able to use logarithmic rules to get to this stage whereby we know very well that ln k sigma p to the power of q, we can introduce a plus in between since these two things are multiplying each other. K sigma multiplied by p to the power of q. I allowed p to the power of q to be alone because p, the relationship is between p and theta, so I want p to be alone. So now, using the logarithmic rules, and which ones did I use here? Because sometimes you might wonder there. I used the law that says ln a times b is equals to ln a plus ln b. So having that used that rule, this is what I have used that as a rule. I said ln theta is equals to ln k sigma plus ln p to the power of q. Now, again, I go to the next stage where I use another logarithmic rules. I say, this one now says ln a to the power of c. It is the same thing as saying c ln a. So this is what I did here, as you can see. This is what I did here. It was originally ln p to the power of q. So where I had ln p to the power of q, I now made it q ln p. So then below this, I wrote this linear equation, the equation for a straight line, which is y is equals to mx plus c. But then I wrote mx below q ln p. Why? Because ln p is the one with the function which is containing p, and ln theta is the one with the function containing theta. So having done that, we always know also that on the y-axis, that's where we put the dependent variable, and on the x-axis, that's where we put the independent variable. So ln p, in this case, since it's a function of p, we cannot put p alone. It's impossible to separate p from ln p there. Ln p corresponds and can be put on the x-axis. Ln theta can be put on the y-axis, which means that ln k sigma is equals to c, the y-intercept, and then m is equals to q. Remember the question, why are we even interested in all this? Remember the question said that we were supposed to ultimately find the values of q and k. So we want to be able to find the values of q and k using what we are talking about here. Now, remember that it is suggested that this relationship here, it is suggested that this relationship is correct. So if this relationship is correct, if we take the values of theta and the values of p, and we find their logarithms, ln theta and ln p, if this relationship is correct, then if we draw a graph of ln theta and ln p, that graph must be a straight line. Because according to what we have achieved here, we have achieved to show that ln theta is equals to ln k sigma plus q ln p, which obeys this equation of a straight line. So if the equation that we are given, which we are testing, the suggested equation is correct, then the graph to be drawn between ln theta and ln p should be a straight line. In that regard, then we say this point now.